So if you roll more than 3.5, your set of opportunities, if you would like to go higher, are 4, 5, and 6, because you only have 6 different values. Okay. And what is the probability that you stop in your first roll, or you go into the second one? .5. That's great, Fabio. Why is that? Exactly. So if you want to go on the second roll, that means that on the first one you either got 1, 2, or 3, which is half of your set of opportunities. So it's 0.5 of probability in order to stop on the first one or go to the next one. So by that logic, what we'll do is that the expected value, the expected payoff that you'll get if you roll twice, is there is a 0.5 probability that you stop on 3.5, so it's 3.5 times 0.5 plus what is the average value of this new set? Five plus 5, 0.5 probability. And with that, I think it's 4 something, 425. So by that logic, remember, they asked us for a 3-roll game. When would we want to roll again if we have the opportunity? Under 3? Why would it be under 3, Carlos? If it's 4 or less, yes. So basically, if your average value for 2 rolls is 425, that means that 1, 2, 3, or 4 are less than the average that you might think you can get. So if you get 4 or less, you might want to roll again. So the same logic applies. If you roll 4 or less, you roll again. If you roll more than 425, what is your set of opportunity? The numbers that you want to achieve are 5 or 6, right? By using that logic, what is the probability that you might want to go onto the third roll? Why roll again? Because if you have the opportunity to roll up to 3 times. However, after each roll, you are given the option of either taking the payoff that you just rolled or continue rolling. So in the first roll, you have 1, 2, 3, 4, 5, and 6. You can roll, and the expected payoff is 3.5. If you, on the first roll less than 3.5, so basically 1, 2, or 3, in your mind, another roll is again, because every single roll is independent, you can get 3.5 on average. and that average is more than what you just rolled, then you get the hope of getting something higher on your next roll. So by using this logic, if we roll again, what is the probability that we are going to roll a third time? Yeah, that is the question. Correct. So what is the probability of rolling a third time? If our set of opportunities are 5 and 6 out of 1, 2, 3, 4, 5, and 6. Yeah, 4 out of 6 is a probability that we won't roll again. So 2 out of 6, which is basically 1/3, is the probability that we will roll again. They won't roll again. I mean, you were right. Sorry. So with, where is it? Yeah. The expected value of rolling 3 times is 2/3 times 425 plus 1/3. And what is our new expected value? 5.5. Great. Because it's the average of our set. And this is for a lot, I think. I don't have the calculation in hand, sorry. Let me do it quickly over here. So that's 2/3 times 425 plus 1/3 times 5.5. This is 4666666. So by using this logic, what is your new set if you want to roll a fourth time? Not quite, Omar. Because remember, your expected value of rolling 3 times is 4.6, which means that your set of opportunity for rolling, so what you're striving for on your next roll, is still more than 4.6, which means 5 or 6. So you would still have 2/3 and 1/3. You're right about the first payoff. Every time I get a number, it can be repeat. Yes, so when you roll, you can always get 1 through 6. However, what you're striving for changes depending on the expected value of your previous round. So basically, if you on average could have gotten 425, yes, they repeat. So if you on average could have gotten 425, what you want to get if you do repeat is more than 425, which means 5 or 6. So in the case of 4.6, it works the same. You want to get more than 4.6, which means 5 or 6. Over time, the 5 will get this discarded as well. Now, there's another question that's not over here, but I want to know if you guys understood. What is the average payoff of rolling infinite times? 6, right? Because you can keep rolling and keep rolling and keep rolling until you have the maximum value, right? So 6. Now, are you guys all with me on this one? This was to understand expected value, basically. Álvaro.
Yes, I'm sorry. I really don't understand the way that the game happened because for example, in the first step you roll the dice, and if you're less than 3.5, you roll it again. But when you roll again,
Correct.
yeah, when you roll again, um, and you play with the you stop the game in the second step if you get more than 40.25, right? Only if you get
Mm-hmm.
5 or 6. But
Mm-hmm.
I understand why you put, for example, in the first step, 5 for times 0.5.
Mm-hmm.
The part, can you explain that?
Sure.
So
So I think what you're so basically, this is not the expected value of the second roll. This is the expected value of the game of rolling twice. I think that was the confusion over here. So if you, on average, on just by doing one roll, you get 3.5. So what is the probability that you are happy with that? The probability that you're happy with that is that if you rolled 4, 5, or 6, which means that it's half of the set, right?
yeah, okay, yeah, I understand. That's 0.5 because it's the last three numbers, right?
Mm-hmm. Then, if you want to strive higher than that, you need to get either 4, 5, or 6. The expected value of 4, 5, and 6 is 5, which means that if you stopped before getting something like 4, 5, or 6, that means that on average, you just rolled once. And by rolling once, you have 3.5 on average. Remember, this is not a simulation of somebody rolling. This is the expected value of what a lot of people might get in the game. If this might be an interest exercise for homework, actually, but I think I've given it before in some semesters before. But if we do this on code, what we would have done is basically we have a variable that is basically a roll, which every round it samples in between 5 or 6 with no replacement. How many numbers we have to sample? One. So we just want to roll once. Now, if roll, I'm just doing pseudocode here. This is not something special. If roll is less than the average value of the roll that you can get on that round, then what happens? You roll again. And so forth until you keep increasing rounds, right? Now, did that help or did that confuse you more?
No, so my question was, you roll the first dice, and in the second,
Mhm.
obviously there also will be the six numbers, but you are like
Correct.
playing with 4, 5, and 6 to get an average. Why that? That is the thing I don't understand. Because
Right,
if
because this is not a simulation of somebody playing. This is so basically, if I know what you said, so that your answer will be correct if the events were completely independent. The thing is, they are not because you're given the choice of rolling again or not. That that data point is exactly what makes this different. So if you were just rolling twice, then yes, the expected value would be 3.5 every single time. However, if you're given the choice of rolling again or not, then that means that you you only roll if the payoff that you might have gotten in the other round or that you got if you were satisfied with that is better than what you can get after. So what is better than three than one, two, or three? The value you expect to win, not the expected value of dice roll. Exactly. That is exactly right value. So this is basically the expected payoff of the game, not the expected roll. It is the
it's like,
expected roll for the first roll because you only have one.
so it's like you only have in the second step, if you roll again, only have the three numbers. If it gets another of the three numbers, you didn't count until you get that. Something like that.
Right. Almost like that.
Oh, okay.
For time, we're gonna leave probably. So this one will be for home. Um, let's try to do at least one of the 5 or 6, and let's do the other 3. So let's do 1 after 2 and 3. What does the strong law of large numbers states, and what are the assumptions for this theorem? Remember, there are 2 different kinds of large numbers. You have the weak one, and you have the strong one. What is the difference in between those two? So actually, Rafael stated one of them, and Sandro stated the other one by just a slight difference in their wording. Yes, that is correct. So exactly. So not well, no. I didn't read the word tense in in Rafael's answer, but then both of them are the weak one. So um, generally, let me write this down for you guys to see. Comment. So over here, so number 2, law of large numbers. So the law of large numbers, the strong one, what it states is that the probability of the limit that n being infinite, so while n approaches and it gets larger every time, the sample mean is equal to the population mean. And what is the probability of this? Is 1. So every single time, this is a strong one. Every single time, if your sample size is large enough, the sample mean will be exactly the same as the population mean. Now, the weak one doesn't state this. The weak one is a little bit on the more conservative side. So the weak one says that the limit n converges to infinite of the probability that the absolute value of the sample mean minus the population mean, so that the absolute deviation in between these two, the probability of it being greater than an epsilon, so a really, really, really small value, is 0. This is the weak one. Okay, so the strong one, what it states is that always, if your population size is big enough, basically your sample is exactly the same as your population if you're using the first moment, which is the mean. The weak one is a little more conservative on that. It says that the deviation shouldn't be more than a really, really, really small value if your population size is large enough. So you can have a little bit of deviation, say positive or negative, but that deviation should really be really, really, really small if the sample size is large enough. Strong is convergence. Strong is absolute convergence, yes. Not just convergence, but it actually reaches that value. So it asks us another thing. What are the assumptions for this theorem? So basically, the assumptions is that your distributions are IID, which means that they are identical and independently distributed. Also, that you need to have a defined first and second moment. That means that the mean actually needs to exist. Some distributions don't have defined means. For example, there's a Cauchy distribution that doesn't have a defined mean. The mean it doesn't exist. Does epsilon have to be a fixed value, 0, and arbitrary number? So epsilon is a mathematical constant that doesn't really have a value. It's just an abstract exemplification that means a really, really small value. So it's not a fixed value. It's abstract more than anything. So IID and the moment 1, which is the mean, and moment 2, they exist. So for the first moment, it means that it has a defined value. For the second moment, it just means that it doesn't diverge. So basically, you cannot have an infinite variance or a 0 variance. Sorry, is that clear? So one counter example for. Can I repeat everything? Last thing. So weak is like tendency. Yes, weak is more like tendency. So the last thing is that what they need to work is that the distributions that they use have to be IID, which means independent and identically distributed, and the first and second moment need to exist. What that means is that the mean is defined and the variance is also defined and different than infinite. Okay. Yeah. Let's move on to number 3. What does the central limit theorem says, and what are the assumptions for the theorem? Okay. Remember the central limit theorem. Not sure. Come on, guys. You saw this in Stats 1 and Stats 2 and Econometrics 1, and now you're seeing over here. You gotta know your central limit theorem, even the general idea of it. And just a disclaimer, it usually gets taught the conclusion of the central limit theorem, but not what it states. Yes, it was about normal distribution. Okay, so I guess I'm gonna take this. So the central limit theorem, what it tells you, random variables tend to normal, any distribution will tend to have normal when it increases. Yes, kind of that. However, the definition never goes with the normal distribution. What the definition is, they talk about the standard normal distribution. The standard normal distribution, which is usually called a Z, is the same as saying a normal distribution with mean 0 and variance 1. Okay, so what the central limit theorem tells you is, like the law of large numbers, we're working with while n increases in size. So when n is large enough, so when your sample is large enough, the probability that your sample mean adjusted by the mean of the population by the standard error of your distribution is less than or equal to one specific value of your distribution is actually, so this is basically the definition of a distribution, right? The less than or equal to one value of your distribution is your standard normal distribution, or what you might call Z. Okay, so any distribution, if your sample size is large enough, adjusted by their mean and variance, should tend to a standard normal distribution. And well, the other question was the assumptions, right? So for this one, the only thing that you need is it needs to be IID. Any question?
Yeah, I was not sure about the central limit theory because I understand that the observations are like the means of a sample, right?
The
And
observations are mean of a sample. What do you mean?
so it's like like a lot of observations. You take the, I don't know, the a very large number of observations you take, and it tends to be a, a, a standard deviation, a zeta, you know? But I was thinking that the observation are not the variable is like the means. The observation are the means. You understand that? Like the means you
No,
use.
I don't really get you.
It's like, can I say in Spanish
Sure,
this
sure,
please?
sure, yes.
Lo que pasa es que yo tenía una duda, ¿no? Porque cuando
Mm-hmm.
ellos hacen de que o sea, la probabilidad hace que tienda a ser una distribución normal Z, ¿no?
Mm-hmm.
Yo pensaba que usaban de observaciones, no la variable en sí, sino la media, observaciones como medias de una variable, ¿no?
Over
Como
here.
estás poniendo ahí. Ajá. No, el X barrita.
Uh-huh. So this one.
Ajá, esa es como tu observación, ¿cierto?
No, so basically what we're saying is that if, for example, these two are the same, then all of these numbers should use 0, right? So this is just an example of something you can put over here. Then it is, so you're correct in which you can put any number over here on the left one, but
Ok.
it was just an example to put the sample mean over there.
O sea, como que podría ser, digamos, las observaciones podrían ser, digamos, observaciones como medias de una muestra o como que observaciones en sí, ¿no?
They could be
Como que,
observations themselves as well, yes.
ok, ya,
So
thank you.
this is the definition, but what you can use in order to do Z is any observation.
Can't, de no poder hacer,
Can.
o no te
No,
escuché.
you can.
Ok.
Let's do one. Yeah, let's do one. I think that is the most thorough on all of them. So what one says is that we have an x that is a normal distributed variable. Lambda is greater than 0. And we have to calculate the values of x squared and e to the power of lambda x on expected value. So first one is expected value of x squared. Now this one should be quite easy for you guys, right? Because you can just apply the regular definition of the variance in order to get this solved, right? So basically, what is the definition of variance, guys? The definition of variance is that the expected value of x squared minus the square of your expected value this is your variance, right? So if you already know your variance, which is 1, and you know already your expected value, which is 0, and 0 squared is still 0, then you have your answer. The expected value of x squared in a, oh, my bad. This is not 0. We are working with, let me put this over here. X tends to the normal mu and sigma squared. Okay, so let me erase this quickly. Okay, so over here, what we have is sigma squared. And over here, what we have is mu squared. Which means that we can get our value for the expected value of x squared. Which is simply sigma squared plus mu squared. Right? Any doubts about that? Because the next one will get a little bit more on the difficult side. Not difficult. You have to see it basically. We're good? Awesome. So for the next one, I do want to first. So the next one is the expected value of e to the power of lambda x. Now, to make our lives easier, but the solution is the same, just to spend less virtual ink, let's say that lambda is equal to 1. Our restriction is that it's greater than 0, but the same solution works. Okay. And also, you have to remember something. The normal distribution is the following. It's 1 divided by 2 pi sigma squared e to the power of minus your variable minus its mean, all of this squared, divided by 2 sigma squared. Okay, this is your normal distribution, and you don't have to forget it, okay? Normal distribution. Okay? When you turn it into the standard normal, it gets easier. Why? Because you just replace every single sigma with 1 and the mu with 0. All right? We can now to the exercise, which I have over here somewhere. Okay. Our exercise is doing the expected value of e to the power of lambda x, and we're saying that lambda is 1. So, what is the definition of an expected value? Do you guys remember that? Not by summation, but the other thing. Remember, we're working with continuous variables over here. And continuous variables have a different definition. Integral, yes. So the definition of an expected value, let me put definitions over here, of y is basically the integral of minus infinite. Here it's really the dominion, but let's assume that it's minus infinite to infinite of y f, the distribution of y dy. Okay, that is the definition of an expected value. Also, one other tip that I want you guys to have is that you can turn any normal, so let's say if x is normal, you can turn it into a standard normal. How? By taking its mean and its standard deviation times its standardized distribution. Okay, that is a really good trick that will help us out throughout this exercise. Okay, I'm gonna separate this. Okay, there we go. Let's do this one, and then we'll do our introduction. So we defined it by using the integral of minus infinite to plus infinite And we're going to change these two things. So lambda, we said that let's make it up to 1. It really doesn't change a thing. And x, we'll make it out to be a standardized normal distribution instead of a normal distribution. The integral is multiplied by f of y, which means that the distribution of y, the marginal distribution of y. Okay, so e to the power of, now it's not x, it's the mean of x plus the standard deviation of x, z, and our normal distribution, which is f, but it's no longer x, now it's z, doz. Okay, so we know what f of c is. F of c is the normal distribution, but standardized, which means that sigma is equal to 1 and mu is equal to 0. And if we have those, it gets much, much simpler. So it'll be 1 divided by 2 pi, and now since sigma is 1, we don't put anything over there. E to the power of minus, mu is 0, and this is no longer x, z. So z squared divided by 2, it's still 2. Sigma is 1, so 1 squared is 1. So z squared divided by 2 doz. So now that we have, it's a good idea every single time you're resolving integrals to take away everything that's not the variable that the integral is resolving. So in this case, what we can take away is the 1 divided by square root of 2 pi. And also, remember that the exponentials are really easy to separate just by multiplying them. So this e to the power of mean can get outside. So we have minus infinite plus infinite. And now inside, we do have some exponentials, which are e to the power of, if you don't know how to get to this step, please let me know. I'm just trying to do it a little bit quickly. Divided by 2 doz. Okay. I just mixed up the over here with the one over here. We good? Yep. Okay, so next thing, we are going to remind you of Maths 0, in which you learned how to complete squares. Okay? So on Maths 0, you learn how to complete squares. All right. Thank you, Facilitador. On Maths 0, we learn how to complete squares. Now, by completing squares, what I mean is that I'm going to put a little asterisk over here, is that this one, we can gather up, put up in a single e to the power of something. That to the power of something is minus 1/2 of z squared minus 2 sigma z. Why I'm putting the 2? Because this doesn't have divided by 2, and I'm taking the divided by 2 out. So if I complete this square, I have minus 1/2 of z squared minus 2 sigma z. And by completing this next square, I'm adding a sigma squared. But in order to add this one, I need to take it out after. Minus 1/2 sigma squared. This is completing squares, basically. It's just a reminder of something you did like 6 years ago. So if I solve this out, it's minus 1/2 z minus sigma squared minus 1/2, because I gotta wrap the squared, minus 1/2 sigma squared. Now we can return to the exercise. So by returning to the exercise, what we get is, again, we have the same thing outside. Two pi e to the power of mu integral of minus infinite to plus infinite of e to the power of minus in everything that I have over here. 1/2 z minus sigma, all of this is squared, plus 1/2, because minus with minus is plus, sigma squared d of z. Am I done? No, I'm not done. But there's a little bit left, don't worry. So the next step is, again, I have to take out everything that's not relevant to the d of z. So this one, the 1/2 sigma squared, doesn't have to be here. So I'm gonna take it out. So this is 1 over square root of 2 pi e to the power of mu plus sigma squared divided by 2. And now I hope you guys see something familiar. E to minus z minus sigma, all of this is squared, divided by 2. D of z. Now, does this resemble anything to you? Hold on. Does this resemble anything to you guys? Oh, didn't. Doesn't matter. Okay, so does this resemble anything to you? Does it look familiar? No? Okay, let me scroll over and show you this. Does this look similar? Or maybe this one. So anyone has a clue on what to do over here? No? Alvaro.
Excuse me, I have a question in the first part. What did you do in the first part of integral uh, when you separate with the C's? Can you explain that, please? Or
So the asterisk
no, the part above that.
here?
Eh, no, a little bit above.
Over
When
here.
you FC and you replace by one uh,
Uh-huh.
one divided by two B and epsilon power
Mm-hmm.
F.
So it's basically your normal distribution. However, since you're using a standard normal one, sigma is 1 and mu
Uh,
is 0. And instead of x, you have z. So it's 1 over
uh,
2 pi times 1 squared, which is basically multiplying by the same thing. X is z, z minus 0, which turns out to be z squared. And 2 sigma squared is 2 times 1, so 2.
it goes the standard is one and no, the
Correct.
variance is one and the mean is zero, right?
Correct.
The parameters.
Mm-hmm.
Okay. Yeah, thank you. Excuse me.
So what Rafael just said is almost the answer. So if you look at this, you have basically the standard normal distribution. You just have one shift. So if you had the distributions, if this is a standard normal distribution, what you have over here right now is a shift towards the left. However, does the area under the curve change? No, it's still the same. So basically, if we evaluate any distribution, and this goes for any distribution, towards all of their dominion, so minus infinite to plus infinite, all of this should give us 1. So that's 100% of their distribution. So all of this is equal to 1. Now I'm not taking into account the rest. This is a parenthesis. All of this is equal to 1. So the whole answer is just 1 divided by 2 pi. So basically what's outside? 2 pi e to the power of mu plus sigma squared divided by 2. And that's it. Why is it 1? Because this is the whole distribution. If you have a marginal distribution like this one, and you evaluate it throughout the whole dominion, then you'll get to 1 because it's a sum of individual probabilities. And the sum of every single distribution, or its area under the curve, is always 1. Because 1 is the maximum probability that you can have. It's 100% of occurrence. So the normal distribution gets rescaled, yes. 1 because you standardized it. And then at the end, what we have is a little shift to the side because of that minus sigma. However, even though we're shifting the distribution, it doesn't change the fact that we're getting the whole dominion. So we have the whole integral of the whole distribution. So it's still 1. Okay, very well. Guys, we're going to jump to R. Okay, so this is how our studio looks. You have 4 panels over here. You have the your script panel over on the left side. You can move these around if you'd like. For example, you might have the environments, history, connections, and tutorial over on the top right, and your console and jobs over here at the bottom left. And over at the bottom right, what you have is your files. So on your window, on your folder that you're open right now, it'll show you the files that are present in that folder, your plots. Whenever you create a plot, it will show over here the packages that you have loaded. So packages are extensions of R. They allow you to use functions that other people have created in order to facilitate your work. Help, which will be your best friend. This is, for example, a function I've created. So help should look over like this. And over here, you can write anything. So let's say we mentioned sample the other time. So you write sample, and it tells you what variables they used, what each argument signifies, the details of the function, and it tells you also examples on how to use them. You will always use the help. And the viewer is very similar to the plot. However, the viewer allows you to see interactive elements and HTML elements. All right, so let's get to the introduction of this. First of all, you'll want to create a new script. Over here, you can create a new script by doing 2 things. One is file, new file, and R script. The second one is over here, this icon with a plus. You can just create a new file and click R script. And you can write anything on it. However, if you want to run a line, you have to do Control Enter. Now, it doesn't understand what is gibberish is because it is gibberish. Let's get on how R understand things. So for example, you can do comments by writing up hashtag and then any single string of text. And you can do simple calculations, say 3 plus 4. You do Control plus Enter. And over on your console, you will see the output. So it is like your do file, yes. You will see your output. So my output is a vector of 1 in which the first entry is 7. 6 plus 12, I should get the same, but with 18. 5 plus 5, and you can do several different mathematical operations. You can do additions, you can do subtractions, multiplications, divisions, and it will take into account your parentheses, exponentiation. The modulus operator is very similar to what you may have done in introduction to informatics. So what the modulus operator is telling you is if you divide this first number by the second one, what is the residual? So 28 divided by 6 is not an integer. So what is the closest value that you divide by 6 and you get an integer? It's 24, right? 24 divided by 6 yields you 4. Now, how many numbers, how many spaces are there from 24 to 28? 4. So the modulus operator, for example, is a really good way to find complete divisors of a number. Say, for example, if you want to know if a number is odd or even, that is really simple. You just do the modulus of 2 of any number. So, for example, 5 modulus of 2, you get 1, which means it's not even, it's odd. If you do 6, it's even, because the residual of dividing by 2 is 0. Okay? You can assign values to any single variable. The variable doesn't have to be one single letter. You can give it a string of text. So for example, and if you want to do this symbol easier, I mean, you can just type out, which is the less than symbol and a dash, or you can do alt plus dash. Okay, that is to do it faster. So alt plus dash yields you the symbol on our studio. So if we assign this 42 to the x value, we're going to create a value called x that represents the number 42. Now, if we just write x and print it, we get 42. Again, we can use not just one character, we can use several. So my apples, if we print out my apples, we'll get 5. You can have several variables at the same time. Dash, so the minus. And if you have multiple variables, you can do operations in between variables. So my apples plus my oranges is the same thing as doing 5 plus 6, 11. You can also assign operations in between variables to other variables. So for example, my fruit is my apples plus my oranges. And we also get 11. However, this 11 is now connected to my fruit. There are different types of variables. Now, the first one that we already seen is numerics. I'm going to do my numeric, which is 42. There are also characters. So characters are strings of text. So my character is universe. Look at my environment. It puts it in between quotes. That is the way to assign text to a variable. There are also logical variables, so true or false, and you have to write them in capital letters. We have these 3 different types of variables: numerics, characters, and logicals. Let's see how we can know which variable each of which class. Control plus enter. If we use the function class, and how you use functions is you write it, you give it parentheses, and inside you put the arguments. Now class takes a single argument, which is an object. All of the variables and values that we create are objects. So if we do class my numeric, it's going to tell me that it's a numeric variable. Character is going to tell me it's a character variable, and logical will tell me it's a logical. Now, we can do operations not just with single entry variables. We can have multiple entry variables. The first level of multiple entry variables are vectors. So vectors. So since Rafael told us that he was very inclined to go to the casino, let's do an example with Vegas. First of all, we'll have a numeric vector. And how do we define vectors? We use the C, which means concatenate. This term might resonate with you from Excel. You concatenate different values or strings or logicals. So if you want to create a vector that's 1, 10, and 49, you do C, 1, 10, and 49. And if you look at the environment, the numeric vector says numeric 1, 2, 3, so it has 3 entries. And the entries are the following: 1, 10, and 49. The same as a character vector that we just created. The difference is that the entries are characters and the type is defined as character. We can do the same with a Boolean vector. Booleans are defined as logical values. So again, let's go back to the casino. If we wanted to know what is a summary of our week on Vegas, and let's say we played poker and we played the roulette, we're just going to put our winnings from Monday to Friday of poker and of roulette on different vectors. Okay? We are also going to create and assign a vector of characters to our numerical vector. And how do we do this? We're going to use the names function. So the names function allows us to modify the names of a specific entries on our object. So for example, our poker vector and our roulette vector, they have 5 entries. So we have to give it 5 names. Now, in order to represent them correctly, 140 will be Monday, minus 50 will be Tuesday, and so on until Friday. So if we assign this character vector to the names of our object, then if we look at our poker vector, then we'll see that every single entry is named. Likewise, our roulette vector. Okay. We could have done this the same, because remember, variables are completely replaceable. So that means instead of doing this whole string twice for this guys, we could have assigned this character string, this character vector, to a variable and then assign that variable to the names of our objects. So instead, we're going to reset our vectors so they are now numerical. Remember, named numericals. And now we're going to create a days vector and assign them to the names of our objects. And we'll get the same result that we had before. Everyone's following? Yeah? Okay. Please, I know it's 11:30, but give me like 10 more minutes in order to finish up with vectors, and then we'll continue over at the workshop. So imagine that you have two vectors, A vector and B vector. You can do operations with vectors just like you could with variables. So if we take the sum of these two vectors, what it's going to do is sum the elements of each of the entries. So A plus B, just like doing math, should be 1 plus 4, 5, 2 plus 5, 7, 3 plus 6, 9. And that is what we're going to get over here, 5, 7, 9. Okay. This is just to remind us that we are at Vegas. We did this 4 steps that are necessary to be over here. So how do we know each of the days how much did we win or we lost? We can take the sum of our winnings from both vectors, from both games, and get the total daily. So on Tuesday, we lost money, and on Thursday, we lost money again. Now, how do we know how much we won or how much we lost throughout the whole week individually per game? We use the function sum. The function sum is like summation of all the entries on our vector. So that means that poker vector has this 140 minus 50 plus 20 minus 220 minus 120 plus 240. And we sum all of them and we get the total of poker. We won 230. We do the same for roulette and we get that we lost 314 with roulette. We want to know overall how we did. So our week at Vegas ended up being a negative week of minus 84. But hey, you maybe had fun. Okay. We can also do logical operations, so in equations. For example, we can check if the total of poker is greater than the total of roulette. Now the total of poker is 230, the total of roulette is minus 314, which means that this equation should give us true or false. Which one is it, guys? True, correct. So if we run this, we get true. And remember, these logicals always have to be capitalized. R is cap sensitive, which means that A is not the same as A. For example, if I do this, I'm gonna get false because they are not the same. Okay. How do you go in between managing individual entries of vectors? So for example, we can open these brackets and indicate that we want the third element of poker vector. Now poker vector has these 5 elements. If we want the third element, means we want Wednesday. So this is 20. So poker Wednesday should give us 20. Another way of doing this is by giving it a vector. So poker midweek should give us 2, 3, and 4, which are Tuesday, Wednesday, and Thursday. Tuesday, Wednesday, and Thursday. Now there's something special about the vector that we created. We gave it names. Since we gave it names, we can subset, that's how this is called, by not only by using the positions of the entry, but also by doing the names of the entries. So for example, if I wanted Monday, Tuesday, and Wednesday, I can subset by a character vector, and I get Monday, Tuesday, and Wednesday. So another thing that I skipped real quickly is that instead of doing C 1, 2, 3, 4, 5, and 6, you can do 1, 2.6 if they are connected in between all of them. So if I wanted to get Tuesday through Friday on the roulette's vector, I can just by doing 2 points 2 through 5. Okay. There are also other helpful stats functions like mean, for example. What is the average that I won Monday through Wednesday? So the start of the week in poker, 36.6666. Now, maybe I want to know on which days did I make money on poker? So I'm going, this subset is completely unnecessary, by the way. I just put it over here to reiterate that you could use the 2 points because we have 1 through 5, remember? We have 5 days of the week. So vector and poker vector 1 through 5 should be the same. Now, if we do this, how many of them were greater than 0? We're going to get a logical vector. Now, these logical vectors will tell us if we won money on each of the days. So Monday we won money, Tuesday we didn't, and Thursday we didn't. So if we use this selection vector, remember this is full of true or false, and we use it to subset our poker vector, we are going only to get the values in which our selection vector is showing true. So those are the days that we won money. We can do the same for roulette and get on which days did we win money on roulette. All right? Okay. Guys, I know that I extended myself a little bit. I'm sorry for that. Two things. So the workshop, we're going to start it by doing matrices, which is all of this. And we're going to skip factors, but I'm going to give you this in order for you to study yourself. Then we're going to do data frames. And after that, we're going to start looking at the tidyverse. So tidyverse is a group of packages that help you in the workflow by coding R. Okay. And I know that I went a little bit quick, but thank you guys for staying here. The assignment. So do you mean the exercises from the tutorial that are left for home? So they are not an assignment. They don't have a grade. So that's what I mean by they are not an assignment. They are for you to practice. And also you can ask me or Jesus anything about the exercises if you have any doubt. Also, for the exercises, you will need to, I'm gonna upload the solution, but you will need to know the multiple normal distribution. Now, I will upload the formula on the solution, but that is something that I think you guys didn't see at the class that you need to in order to solve the exercises. And that's it. Thank you very much, guys. I'll see you guys at 3.